Yeah, so this is quantum mechanics 101 and we're trying to solve the Schrödinger equation for a hydrogen atom. Now, we all know the state of a particle is described through a wave function, and if you take the modulus square of a wave function, you would get the probability density throughout the space, and if you find that particle at any space, the wave function collapses. But that is too far. To solve the hydrogen atom problem, it is simple one, but also it is quantum mechanics, so nothing is simple. We have to think in a different way. We have already established that if you take the modulus square of the wave function psi, you would get the probability density, and essentially you get this chemistry spikes, the graphs, the 2PSP graphs. What you get, those are the solutions to show the Schrödinger equation. Now I have drawn a sphere, roughly a sphere here, and we know three things. Instead of working with Cartesian coordinates, we cannot work with Cartesian coordinates in this case, because this is 3D spherical symmetry we have gone here. So we have the radial displacement. So a electron is orbiting a heavy nucleus. Electron is orbiting this heavy nucleus, and the nucleus is situated through a r distance, so the radial distance from the origin. The azimuthal displacement, is the angle throughout the equator. The theta is just the angle in the z-axis in this case. Now r goes from 0 to infinity, theta goes from 0 to pi, and psi, the azimuthal displacement, goes from 0 to 2 pi. And if you plot this graphically, you'd get a standing wave functionality for a sphere, and essentially this is the solution to the spherical harmonics. The spherical harmonics are the spherical harmonics. They are what they say. So this is generally drawn through colors, but I have drawn with textures. So let's just assume this is positive. This represent curly, represent the negative, and the white parts are neutral. So this is in respect of spherical harmonics. And if you draw the same thing, towing with the radial, angular, and the azimuthal displacements, and graph them through their radial displacement, so the displacement from their origin, you'd get the spiky, the graphs from chemistry you get. So not only that, so what will be our roadmap, our path to solving this problem? We will get a huge partial differential equation. We will use the separation of variable method to break that partial differential equation into three ordinary differential equations, and those three ordinary differential equations will give us the eigenvalue solutions for the radial displacement, for the angular displacement, for the azimuthal displacement, and an additional eigenfunction solution for the time. In this case, there will be t. I will get to that later. So that is our roadmap. So we have to get the psi for 3 and modulus squared them to get the solutions for the hydrogen atom. So let's get started. This will be part 1 of many videos, because this derivation is very long and it will takes more than 30 to 40 pages for me at least. So it's just easier to explain it for me and you. So we have a psi of r, theta, phi, and t. Through the roadmap, we know we have to break this down into the eigen solution, which is psi of r, angular displacement, and the azimuthal displacement, and an additional oscillatory function, which is the exponential of r minus I et divided by h bar. This is a very famous equation which will pop out everywhere. And now, so let's get started. We will have the Schrödinger equation for the spherical coordinate system, and for this system we will have the Laplacian. Now if you have taken vector calculus or anything in the differential geometry, will know, and in the spherical coordinate system we will have special expressions for the curl, divergence, and gradient. Essentially the gradient square is the Laplacian, but it's kind of not. You will get that later. So this expression has to be memorized by every physicist going through grad school. No one can do anything about that. So we'll substitute this for in this equation, and we get the whole long as equation. That's why I couldn't write that down, it is too long. So now take the v to the right hand side, we will get v minus e. First of all, multiply everything by minus, so the signs change. Then take the v out to the other side, so it's v minus e, multiply everything by 2m by h bar squared, we get this. Take this expression to the left hand side, you will get minus 2m h bar squared into v minus e side. Now we will do the separation of variable method to break this partial differential equation into three ordinary differential equation, which will give us solutions to the radial and the spherical harmonics. So we will do that. So psi of r theta phi becomes r of r, phi of phi, theta of theta. So theta and phi will be the spherical harmonics, which will be denoted by y of theta and phi, which is written like this. Substitute everything. We know for partial derivatives, the one variable in respect to the derivative will be in the derivative and the other variable will be treated as a constant. So in this case, where is that? Okay, in this case the psi will be broken down into r into y, and this here, this is in respect of r, so r will stay and y will be treated as a constant, and so the derivative rule says that y will be taken out of the derivative, so y gets here. Same as this, theta is part of the spherical harmonics, so y it will be a derivative and r will be taken out, r will be taken out. Done. Now divide the whole expression by ry. You would get 1 by r because y and y cancels out. R and r cancel out, so you will get 1 by y, and r will r cancel out, you will get 1 by y, and this will stay the same. Here you will take 1 by r square out, and you will get this expression equals, take this to the other side, 2m by h bar square v minus e. We've distributed the psi, so there is no psi there. 1 by r, take the r square to the other side, and you will get minus 2mr h. Okay, so this gets simplified to this expression. Now you will see something. If you put the equal sign and put the y variables, everything in respect of y, to the other side, you will get two differential equation, where on the left hand side everything is in respect of r, and the right hand side everything is in respect of y. This thing will be only possible if both sides are equal to a constant. So that is the magic of the separation of variables method. This constant will be equal to L plus L plus 1, and the other thing will be equal to L plus L plus 1, but we had the minus sign, we get the minus sign to here. Now the question may arise, why L plus L plus 1? Now this thing, as the rule suggests, will be equal to any constant. This could be c, this could be e, any arbitrary constant, but we know the solution to the Schrödinger equations. Every physicist has tried it. So as the solutions are known to us, we use this to simplify it for us, because in the later equations to find the L times L plus 1, it is just too much rigorous work and nonsense, useless work. We will just write it in this way, and no further work will be needed. So for the part 1 of the video, I will get to this part where we divide or separate the original partial differential equation into two ordinary still one ordinary differential equation and another partial differential equation, and for the later parts we'll divide this into two equations and get the radial, azimuthal and the angular solutions. So part 2 is coming.